Good day, everybody. So finishing up this chapter, or at least the physics portion, in chapter 5 on electricity, current and resistance. So I'm going to know what these two things are, be able to calculate them, and just have a general idea of what they are. So current is the flow of charge. And anytime we talk about a flow, we're always talking about something over time. Like we had a volume flow rate, that was volume over time. I guess that was the only flow that we had. But here we have a current. It's a flow of charge, and it is a charge over time. And so this is going to be Q divided by T. So if we think about a wire, there are all these electrons in the wire. These electrons are able to move freely within the wire. They're called conduction electrons. They're able to move. And so if I have a current, those charges, I'll have a certain amount of charge moving per unit time in that wire. So usually this refers to electrons moving through a wire. Though it can really refer to any flow of charge. But as far as we're concerned, we'll talk about it in terms of a wire. Though later when we discuss the flow of cations and anions across the cell membrane, we can describe that in units of current. The unit is an ampere, or an amp. It's capitalized when it's abbreviated, or capital A. You might see this unit on some of your electrical devices. A resistor is a device that resists the flow of electricity. You can think about the resistor as a pipe with water flowing through it. A resistor is not a pipe, but we can think about it in that way. And with a pipe, if I make the pipe longer, then what happens to the ability for you to push water through it? So if I have a short pipe or a long pipe, which one of those is harder to push a fluid through? Well, it's going to be more difficult to push water through a long pipe. So if I increase the length, if L goes up, then the resistance to the flow will also go up. What about if I have a narrow pipe? If I make the pipe narrower, like going from here, where it's really big, to over here to where it's smaller, then if the area goes up, then the resistance will go down, and vice versa. If the area goes down, the resistance goes up. So a skinnier pipe is harder to push a liquid through. And that's true for electricity too. That I have these relationships between L and R. R is proportional to L, and R is inversely proportional to the area. So the equation for this is rho L divided by A. And here rho, the Greek letter rho, it looks sort of like a P, but it's the Greek letter rho. I can tell, by the way, because it doesn't have, it's sort of rounded on the top and it's rounded down here. Here rho is the resistivity. This is different for different materials. Wood has a high resistivity. Can you think of some things that would have a low resistivity? That is, things that do not resist the flow of electricity very well. Well, most metals, copper, for example, which we use in our homes. We've used different, you can use different metals, you don't have to use copper. In fact, in the early 1900s, people would use aluminum wiring, but aluminum wiring catches on fire easily, so that's why we no longer use that. You can use gold wiring if you're so inclined. Gold actually conducts electricity very, very well. The current is dependent on both the resistance and the potential difference, or the voltage. Now, what do you think is the relationship between R, V, and I? So I, if R goes up, if the resistance increases, what happens to the current? And if V goes up, the potential, or the energy per charge, what happens to the current? Well, if R goes up, the current will go down, because now I'm resisting the flow of electricity, so my current will be decreased. If the voltage goes up, which remember, the voltage is like the energy. So if I give my electrons more energy, what do you think is going to happen to the current? You probably guess okay, that if I increase the energy of my electrons, that they're going to travel at a faster rate. They're going to flow with a greater current. So I have this relationship between V and R and I that looks like this, where I and V are directly proportional, and R and I are inversely proportional. This is called Ohm's law. Often it's written like this. Those are the same. By the way, I don't know if I've shown this yet, but this is the symbol for a resistor, and I have shown you this is the symbol for a battery. And so this would be a circuit diagram. You may see a circuit diagram on your exam. It'll be as simple as this one. For example, if this was 12 volts and this was 2 ohms, what would the current be? Well, I know current is V over R. That's 12 volts over 2 ohms. So that is 6 amps. Electricity going through a resistor will expend energy. Do you have a hairdryer or a bathroom heater at home? That coil of wire that's inside of your hairdryer, so if you look down the pipe of your hairdryer, looks sort of like that, you'll see like this coil of wire that goes around. The wind comes out the middle of it, and that coil of wire, when you heat it up, turns red or glowing. That's basically a resistor, and when you run a current through a resistor, it expends energy. And this energy, which is U, is equal to Q times V. Because you remember, V, when we defined energy, or defined voltage or potential, it was energy per charge. And what is energy? We call that U, and charge is Q. And so the energy is just the U is equal to the product of Q and V. And since power is energy over time, we learned that in the last chapter, I think. Then that would be U divided by T, or Q V over T. Look at this. What is this Q over T? Well, that's a charge over time. That's going to be a current. So P is equal to I times V. That is for the electrical power of a device. Electricians use this a lot to calculate the power that's required for a particular circuit in a home. So for example, a light bulb that operates at 120 volts and has a current of 2 amps, what would be the power of that light bulb? Well, power is equal to I times V, so that's 2 amps times 120 volts. That would be equal to 240 watts. So that's a fairly bright light bulb. Electricians do this a lot, for example, when they're building your house and designing the electrical system. You have lots of different circuits in your house, and they have to design the circuits so that they have the appropriate capacity to run all your devices. So, for example, let's say that you have a bathroom heater. A bathroom heater, they would say, has a power of about 1,000 watts. For the sake of this, let's say that it operates at 100 volts. It actually operates at about 110 volts, but just to make the math easier. And so they would say, well, how much current is that bathroom heater going to pull? And so they would calculate and say, well, it's power over voltage, 1,000 divided by 100. So it's going to pull a current of 10 amps. I would expect a question like that on the exam coming up. Okay.